So this is a continuation of evolutionary solvers and how we can use those in Grasshopper. And I've imported a surface into Grasshopper. And so I'm not going to show you what the surface looks like because we're going to use it as one of the fitness landscapes. So if this is, say, a fitness landscape for an evolutionary solver, what sort of information can we pull out of that? So say we have this surface and we want to find the highest point on it. So we can evaluate that surface. And maybe we use a multi-dimensional slider. And you can see as we're sliding around, there's some height values that we can get. We don't exactly know where the highest value is. We could kind of dance around here until we get something that might be a high value, but we don't know if that's the highest value. So what ways can we sort of take advantage of Galapagos or understand that a little more specifically? So instead of using a multi-dimensional slider, we can also evaluate it in terms of, say, a vector. And we'll plug just a couple sliders into that so we can evaluate these points independently. Okay, now these become our genome, right? So we have an X and a Y direction. You can evaluate separately. We might even want to add a finer resolution of that. Okay, so then to that we can try to say what is the height value of some of these things. So as we're getting some geometry out of this, we have a fitness criteria. So we can say what's the highest point on this surface. So we can use Galapagos. We can say this is going to be our fitness criteria. These are our genomes. And we can try to, say, maximize that. So it's just around the surface, it's sort of finding high points, testing mutations to see if there's a local maximum that it's responding to, and sort of narrowing this down in some ways. Now, one thing we do know is that since there's a plane on here, the plane should be relatively flat at its highest point, if the highest point is like the top of a hill and not still on the slope where the surface is cut. So you can see it's roughly 10 units tall at its highest point right now. you can do more iterations if you don't show as many of them, so it won't jump around as much, but you can do a much faster calculation like that. So this is almost 50 iterations of probably 50 different points. It stopped at solver. We'll say that this is that point. Say okay. Now we're going to go ahead and bake this one out, or we'll just internalize this one so we can come back to it. So let's see what else we can get from this this information. Well, we can say we have this surface. Let's populate it with some geometry. And right away you can kind of see what that surface is doing. So I'll just turn those down so we have a set of 5. And then maybe I want to test what point is, say, the furthest away from these points. Just to most of the points. Now, if we want to do that, we might want to say what's the say surface closest point, or sorry, the closest point. All of these points, and we can use this distance. So evaluating that surface to determine where along that surface would be furthest from each one of these points. So in that case, instead of the z value, maybe we can use our distance value. And we can start that over again. We'll try to run through that as fast as possible. The longer we let that run, the better the sort of accuracy of that is. So I'll go ahead and stop it ahead of time. Say, okay, so this point can be furthest away from all of those other points. So let's see if we can visualize that in some way. So I'm going to make a grid of points, trying to recreate our fitness landscape. Sorry, let's make a rectangular array. Start with the point, and I'll go ahead and make this rectangle of 1 by 1, and we'll make it 50 by 50, or 51 by 51 to actually make it fill the 50 by 50 square. So So we can use these to start evaluating or creating a surface that represents our fitness landscape. So if we want to use those to represent our map surface, these represent the sort of variations of the X and Y genome. And if we want to use distance, we can take this distance and then map it to, say, a height. So if create a point, we'll take the X and Y from each one of these points and map the Z from the distance. Now we need to plug these points into this so you can see that sort of grid a little easier. So this is the fitness landscape. This is not the surface that is drawn, but this is just representing the distance from those points. So let's make a surface out of these points so you can visualize that. It's roughly 50 by 50. Or sorry, 51 by 51. And you can see that surface is, if you look at it in top view, is roughly our Voronoi pattern that we've seen before, right? So all of the points inside this sort of cell is that closer to this one, all the ones of this one is closer to this one. And then when we look at that in 3 dimensions, you have these sort of conical shapes or intersections of cones. And so ideally, the distance that would be furthest away from all of these points would be along these ridge vectors where it gets highest. And looking at the surface, you can see that it's going to be over here somewhere. So we can take these points and create the surface to somehow give us a fitness landscape representing that. Now, if we want to see, this is sort of building a new sort of function from that information, utilizing these points. Now, the original surface, if you look at that, is not these points. It just has these points sort of populating it. If we wanted to see where the highest point was that we got before, it would be there. And if we wanted to use, say, the distance from these points to find out where the farthest distance was, we can do the same thing with this. Which should be there. So if we turn on our Voronoi pattern, is basically saying the highest point of that ridge would be our furthest point from any of these other points. So you can see how you can use evolutionary solvers to solve some, say, simple questions, multi-dimensional questions. And these are simple examples that have just two sort of genomes, and they would be useful for much more complex genomes that we might be able to get 4, 5, 6, 10, 12 genomes, all adjusting them independently to find out what that solution space is. Now, it's incredibly difficult to visualize a 12-dimensional space, and so Galapagos can solve more complex situations than we can visualize, which makes it pretty useful for some situations. Keep in mind, as I said before, it's a really slow process. So as you add another genome, these calculations become exponentially more difficult to do, or just more costly to do, because each iteration you add another set of variables that you have to test with all sort of variations of that slider. So it can be useful in some situations and others less useful, depending on if that information sort of fits within the sort of evolutionary solver sort of methodology of working or thinking about things. So hopefully you can use these for some situations to solve or to optimize solutions that are difficult to understand or difficult to visualize within our sort of 2 or 3-dimensional understanding. Thanks.